An H-bridge is a circuit configuration that consists essentially of 4 switches arranged in such a way that you can reverse the polarity to a load, most often a motor, and on control boards and appliances is most often used to open or close refrigerator dampers and lots of other functions. On this circuit board I've got 4 switches, a DC motor and a blade, and a 12-volt source. If I wanted to cause this polarity right here, I would simply close switches S1 and S4, and we would have the negative side appearing here and the positive side appearing here by closing these switches. So by closing switches S1 and S4, motor turns clockwise. If, however, I wanted to do the opposite and cause this polarity here, I would close switches S2 and S3. Now we'll go counterclockwise. Most often on control boards, you would not have this awkward configuration of switches, of course, but you would have a semiconductor version like this. This is a semiconductor implementation of an H-bridge, where 4 transistors are used as switches. 1, 2, 3, 4. We have a couple of transistors here that are used for pre-drivers and logic so that the specific outputs of a microcontroller can select the appropriate switches for the polarity reversal. So in reality, most H-bridges on control boards are going to be in IC form, but this shows how that is implemented internally, and as well how the relatively low voltage and current of a microcontroller output can, in effect, control loads with much higher voltages and currents. So with this 5-volt signal here, I can turn this transistor on, enable switches S1 and S4, and with this signal here, with the logic high of the microcontroller, 5 volts, I can enable switches S2 and S3, effectively reversing the polarity to the load. Over here, we have a 5-volt source that represents the microcontroller input, and of course we have our 12-volt source to supply voltage to the motor. So in effect, controlling the motor direction can be done with simply 2 control lines from the microcontroller. By pressing this button here, this effectively closes switches S1 and S4 and causes the motor to turn counterclockwise. If I want to turn the motor clockwise, the microcontroller would essentially send a logic 1 or 5 volts out of the other port, which effectively closes switches S2 and S3. Not only can you control the direction of a motor using a semiconductor implementation, but you can also control the speed using pulse width modulation. I've now replaced the 5-volt input with a pulse width modulation source that represents a microcontroller using pulse width modulation to not only control the direction of the motor, but also the speed of the motor. So if we wanted the motor to go counterclockwise but to go very slowly, I'm now using a 20% duty cycle to go this direction. I can use that same pulse width modulation to cause it to turn clockwise. So this is a pulse width modulated signal right here. It's a 20% duty cycle. And that's the resulting speed of the motor. If we wanted to increase it to 30, 40, even 50%, of course the motor is going to respond accordingly. If we go more toward 100%, you're going to have full speed. So that's how you can control, with a semiconductor H-bridge, not only the direction, you can also control the speed of the motor. A practical implementation of doing so might be that just before a damper or some type of an actuator closes, that you would want to slow it down for a more gentle closing. That's it for this video. I hope you found it interesting and informative. If so, please give it a thumbs up and subscribe to this channel.